All right, so we're going to keep it moving with the solutions to the practice exam number 1. We are on question number 4. We have lowercase f and uppercase f, of course, representing PDF and CDF of a random variable x. The conditional PDF of x, given that x is bigger than x naught, a fixed number, is defined in this way, called the hazard function, which you will see in survival analysis, reliability, and other contexts. And what we want to do is we want to look at the hazard function and look at a couple of properties. Now, real quick, if you notice the way that this is expressed, it is a quantity that hopefully should make sense. In other words, if you think about the way that conditional probability is found, usually this expression is a little bit different because it's kind of a conditional PDF, whereas we usually have a P there instead of an F. But if you think about F being a notion of probability at a point in an instantaneous calculus kind of way, then everything does come together in this definition. That's not our goal here today. Our goal is to just solve this problem. So let's go ahead and solve it. Part A, show that it's a PDF. Okay. So for part A, we need to show two things. We need to show that it is non-negative and, of course, all important, integration is 0. Okay. So note that every PDF is bigger than or equal to 0 because it's a PDF. And 1 minus f of x not be bigger than 0 since for every CDF it lives between 0 and 1. Okay, so that shows that the entire quotient is non-negative. Okay, let's take it from there and look at the next item, which is demonstrating that this thing integrates out to 1. The integral from x naught to infinity, which is the support of this thing, of f of x given x bigger than x naught dx is going to be the integral from x naught to infinity of f of x all over 1 minus f of x naught dx. Big question, what is constant in this context? The constant in this context is x naught. As you can see, it's a limit of integration. You can see our variable of integration is dx, not dx naught. So x naught is a constant. I'm just going to pull it out. So we just have this integrating from x naught to infinity of f of x dx. Okay, but if you pay attention, realize what's going on. This is 1 over 1 minus f of x naught times 1 minus the integral from negative infinity, or in this case 0, since we know it's supported on the non-negative real numbers. So I'll just go ahead and write that one time and say 0 to x naught f of x dx. But this right here should look familiar as a definition of the CDF. So this is 1 over 1 minus f of x naught, 1 minus f of x naught, which would be 1. Okay, so this indeed is a PDF. Part B, suppose we have a gamma 1,7 random variable, and as soon as you see that, you should be thinking of the other way, more succinct way of writing that, which is x tilde. Okay, the more succinct way of writing that is x tilde exp 7. So our f of x is x 1/7 e to the minus x over 7. Okay. So we want to find the conditional expectation of x given x is bigger than x naught. In other words, we know that this expectation is going to be the integral over the entire domain of the random variable of x times the conditional PDF. Okay, now we know for this situation, this conditional PDF is defined by the CDF and the PDF, right? And we have a specific distribution that we want to work with in this problem. So let's go ahead and find what the CDF would be. We already know the PDF. All right, so here's our CDF. And again, I'll make it even more explicit by saying, well, this is equal to the integral negative infinity to x naught. I'm sorry, x naught to infinity. So again, I'll make it even more explicit by saying, well, this is equal to the integral from x naught to infinity of x times f of x divided by 1 minus big F of x naught dx. Okay. So we got the little f, we need the big F. Just making it explicit that that's what we need for in this problem. Our big F of x is integral from 0 to x naught 1/7 e to the minus x over 7 dx. Antiderivative is going to be negative e to the minus x over 7. Go from 0 to x naught, and we'll end up with 1 minus e to the minus x naught over 7. Okay. All right, so if we incorporate that into this problem, the expected value we're looking for is going to be the integral from x naught to infinity of x times our PDF divided by the complement of the CDF evaluated at x naught. So the complement of this evaluated at x naught is just going to be e to the negative x naught over 7 dx. Okay, threw that color in there just to make sure you're awake. So I'll bring in, or bring out rather, the constant term of e x naught over 7, integrate from x naught to infinity of 1/7. I'll bring that out to x e to the minus x over 7 dx. Okay. I'll go ahead and use the integration by parts. U is x, dv is e to the minus x over 7, du is dx, b is negative 7 e to the minus x over 7. And of course, integral of u dv, uv minus integral v du. All right, go through all of that and end up with 1/7 e to the minus x naught over 7. Okay, we have our uv, which would be negative 7x have our uv, which would be negative 7x e to the minus x over 7 from x naught to infinity V du will end up being a plus integral of x naught to infinity. V du is 7 e to the minus x over 7 dx. Now that can be integrated fully, and I'll let you fill in the blanks, but we end up with an answer of x naught plus 7 as our expected value. All right. Okay, so that's going to be it for the showing that f is a PDF, integrates to 1 is non-negative, and then also using this conditional density to find something like a conditional expectation and identify the value as x naught plus 7. Alrighty, so let's see if we can squeeze this last one in here. We have x is equal to normal mu sigma squared. I should say x is distributed normal mu sigma squared. And we want to transform x to achieve a normal 0-1 distribution. Of course, we're going to let z is x minus mu over sigma. We spoke about this earlier. This is a transformation. So what we're going to need to do, we're going to need to solve for x. This is our g of x, so to speak. Therefore, our g inverse of x is when we solve, g inverse of z rather, is when we solve. Therefore, our g inverse of z is when we solve for x, right? Which is going to be mu plus sigma z. All right, our univariate transformation is our f of z is going to be fx evaluated at g inverse of z times the derivative with respect to z of g inverse of z, absolute value, and then we shift the support accordingly. Okay, so our f of x is going to be 1 over radical 2 pi sigma e to the minus 1 over 2 x minus mu over sigma quantity squared, negative infinity less than x less than infinity. Accordingly, our fz of z is going to be 1 over radical 2 pi sigma e to the minus 1/2. Instead of all of that, I'm just going to put a z, quantity squared. That's how we translate that part into a z. If you want to go through all the steps, you can take this x and plug this x in there, and you'll see you get just a z when you at the end of the day. We're going to multiply that by the Jacobian. That's derivative with respect to z of g inverse, which is mu plus sigma z. All right, the support, negative infinity less than g inverse less than infinity. Okay, we can see that the derivative of mu plus sigma z with respect to z is going to be sigma, and thus this part over here is sigma, which will cancel with this sigma. We're left with a 1 over radical 2 pi e to the minus 1/2 z squared, and the support would be negative infinity less than z less than infinity when we solve for z in this equation. This leads us to the reality that z is normal 0-1 as expected. All right, so that is midterm number 1, practice midterm 1. You can expect a similar vibe for the actual midterm. Definitely some normal distribution stuff, definitely some bivariate transformation, univariate transformation, and as we said earlier, discrete random variable. All right, so stay focused and get those 10,000 hours in.